Welcome to Caltrans LSIT LS exam preparation course. One aid in your preparation for California licensure examinations. A word of caution, don't use this course as your only preparation. Devise and follow a regular schedule of study which begins months before the test. Work many problems in each area, not just those in this course's workbook, but problems from other sources as well. This course is funded by Caltrans, but you and I owe a profound thanks to others, the course's instructors, from the academic community, the private sector, other public agencies, and from Caltrans as well. We wish you well in your study toward becoming a member of California's professional land surveying community.
Welcome, viewers, to this unit of the Caltrans training videos. My name is Edward Zimmerman. I work at in the Geometronics branch at Caltrans headquarters in Sacramento. In the past, I worked for the California State Lands Commission, a private surveying firm, and the city of Sacramento. I also teach surveying at Sacramento City College. I am licensed as a professional land surveyor in California and in the state of Arizona. The subject I would like to discuss today is understanding and, most importantly, simplifying and working with basic surveying mathematics. I want to emphasize that this video unit's objective is to present basic mathematical skills useful to surveyors. The discussion will be limited and is not intended as a comprehensive presentation of all surveying math procedures. It is taken for granted that most viewers are already familiar with some or most of the topics presented in the beginning of this unit. An understanding of basic arithmetic, algebra, geometry, and trigonometry calculation methods is necessary to understand the more complex forms of mathematics that you will eventually encounter in your surveying career. Hopefully, this unit will help the surveyor and the trainee to develop and hone their computational skills and to make correct and effective use of appropriate solutions to particular survey calculation problems. I am assuming that the viewer is comfortable using and performing basic arithmetical operations. A review of the technical math texts in the reference section of this workbook will provide additional help with operations and fundamental mathematical skills not covered in this video. In this day and age of electronic marvels, every surveyor has one or several types of computers and calculators. This video will present various principles of math to give the viewer a familiarization and a better understanding of the principles involved in solutions. It is assumed that a calculator will be used to determine numerical values of any given problems. The development of the decimal system can be tracked back many centuries. In ancient times, a small group of objects were counted by comparing their number with the number of fingers on one's hand. When larger groups of objects were counted, pebbles were arranged in groups of 10 to keep track of the large number of objects being counted. The modern counting system, or decimal system, is based on these early beginnings. The whole number part of a number falls on the left of the decimal point, and the fractional part of a number falls on the right of the decimal point. The chart in this graphics shows the value of numbers both left and right of the decimal point. As shown, numbers to the left are whole and follow powers of 10, while numbers to the right are fractional. When adding a group of decimal numbers, tabulate them so the decimal point of each number is in vertical alignment up and down the column of numbers. For example, add 102.21, 1415.5, 21.348, 608.17, 6.411. Starting with the column to the right, total each column, placing the decimal point of the total in line with the decimal point above. When subtracting decimal numbers, also tabulate the numbers so each decimal point is aligned vertically. For example, subtract 1324.465 from 21647.9. Starting with the column to the right, subtract each number and then place the decimal point of the difference in line with the decimal points above it. Notice that zeros have been added to the minuend to fill out the column. To multiply decimal numbers, determine the number of decimal places in both the multiplier and the multiplicand. The product will have the same number of decimal places as total places in the two factors. For example, multiply 843.21 by 56.893. The product will be 48,048.63543. In the second example, 0.043 is multiplied by 0.0021. Note that zeros must be placed between the product and the decimal point to create the correct number of decimal places. Long division of decimal numbers is set up and tabulated the same as whole number division. For example, divide 2,467.89 by 10.45. Move the divisor's decimal point to the right enough places to make it a whole number. Move the decimal place in the dividend the same number of places to the right. Position the decimal place in the quotient directly above the decimal point in the dividend. You will generally have to add zeros to the dividend to attain the required numbers of decimal places in your answer. In the surveying measurement process, it is important to indicate the accuracy of a measurement by recording the correct number of significant figures. The number of significant figures in a quantity are defined as those digits that are certain or directly read plus one digit that is estimated and or uncertain. Significant figures are sometimes confused with decimal places. Decimal places do not indicate significant figures, but are used to maintain the correct number of significant figures. Some examples are being shown in this graphic. In surveying calculations, it is important that calculations be consistent with the measured values. In addition and subtraction operations, answers should be rounded off to show the same digit as the digit expressing the least significant figure in the column above, as shown in this graphic. As shown in this next graphic, in multiplication or division operations, the least number of significant figures in the answer should not exceed the least significant figures in any of the factors. Rounding off numbers is the process whereby one or more digits is dropped from a number so that it contains only the required number of significant figures. When rounding off numbers to a required degree of accuracy, one of the following methods shown on screen may be used. First, when the digit to be dropped is less than 5, the number remaining is simply stated without the digit. Second, when the digit to be dropped is exactly 5, the nearest even number is used for the preceding digit. This method establishes a consistent pattern and yields a better balance of results. Last, when the digit to be dropped is more than 5, the nearest preceding digit is increased by 1. Simply stated, percentage is an indication of a number of hundreds to a whole. If a square contains 100 smaller square parts, then each of the smaller squares are 1/100th of the whole, or 1%. A simple percentage problem has three parts: rate, base, and percentage. In the graphic, rate is the percent figure, the base is the total quantity, and the percentage is the quantity of the percent of the whole. Thus, when computed, 10% of 120 is 12. Note that the decimal point in the percent is moved 2 decimal places to the left to yield the correct number for the percentage. There are 3 types of percentage problems. We have already seen how to determine the percentage when given the base and rate. Now let's look at the next one, finding the percent given the base and percentage. In this graphic, let's determine what rate or percent of 840 is 21. Just divide 21 by 840, which equals 0.025, or when the decimal point is moved 2 places right, 2.5%. In this example, the last of our percentage problems, given the rate and percentage, we will find the base or whole. As done in the graphic, change the rate by moving its decimal point 2 places left and divide the percentage by it. 915 is 75% of what number? The answer being 1,220. A number squared is simply a number multiplied by itself, such as 8 times 8 equals 64. 64 being the expression of 8 squared, or the base number raised to the second power. A number that is cubed has been multiplied twice by itself, such as 12 cubed is 12 times 12 times 12 equals 1,728. 1,728 is the expression of 12 to the third, or 12 to the third power. Power is also called an exponent and signifies how many times a base number is to be multiplied by itself. If an exponent is 5, this signifies a number raised to the fifth power. As shown in the graphic, 21 to the fifth equals 4,084,101. All handheld calculators perform exponential operations with simple keystrokes, so we will spend no further time on the topic. Surveyors generally measure linear and vertical dimensions in decimal survey feet, angular dimensions in degrees, and units of area in acres and square feet. However, it is often necessary to convert these measurements to other measurement units, such as decimal feet to feet and inches. I will next discuss conversion operations that will make conversions simple and accurate. First, let's consider the U.S. survey foot and its relationship to the international meter and foot. The official unit of length in the United States is the modern international meter, defined at a world conference in 1959. This created a new definition for the foot in the United States called the standard foot. All surveying prior to 1959 had been done on the old foot, so it was decided to retain it and rename it the U.S. survey foot. The graphic now on screen shows the correct relationship of U.S. survey foot and the new international meter. Any conversion operation regarding meters and survey feet should carefully consider the correct constants. Surveyors normally work in feet and decimals. However, it is sometimes necessary to convert dimensions to feet and inches and vice versa. As shown in this graphic, convert 123 feet, 7 3/4 inches to decimal feet. In the first step, reduce 7 3/4 inches to decimal inches by reducing 3/4 of an inch to its decimal form, 0.75 inches. In the second step, 7.75 inches is reduced to a decimal of a foot by dividing it by 12. Adding the decimal foot to 123 equals 123.65 feet. The reverse of foot and inch to decimal, or decimal to feet and inches, is shown in this graphic. Convert 46.37 feet to feet and inches. First take 0.37 feet and multiply it by 12, converting it to 4.44 inches. This decimal fraction reduces to 4 44/100ths of an inch, or most nearly 3/8 of an inch. Adding the 46 feet back into the conversion completes the operation at 46 feet, 4 3/8 of an inch. The number of decimal places rounded to will be dictated by the accuracy required for the work. During colonial times, the most popular measuring device in the United States was the Gunter's chain. It was 66 feet long and was divided into 100 links, each 7.92 inches in length. As can be seen in this graphic, it was very well suited for surveying work in English units. Converting feet to chains is accomplished by dividing the number of feet by 66. On the graphic, this operation yields 26.09 chains, or 26 chains, 9 links. In this example, we are converting chains to feet. Simply done, multiply the distance expressed in chains and lengths by 66 feet. The previous graphic showed the relationship of area to chain units, or 10 square chains equals 1 acre, or 43,560 square feet. The bottom conversion problem on the present screen converts a rectangular parcel measured in chains to area. The sexagesimal system, or base 67 system of angular measurement, is used by surveyors in the United States and in many other parts of the world. This system is based on a complete circle being divided into 360 parts, or degrees. Each degree is subdivided into 60 parts, or minutes, with each minute divided into 60 seconds, as shown in the graphic. The European system divides the circle into 400 parts called grads. Each grad is subdivided into 100 parts, or centigrads. Centigrads are further divided into 100 parts called milligrads. When using degrees, minutes, and seconds in calculations, it is often necessary to convert them to decimal form and vice versa in order to make the numbers compatible with the calculators being used. For instance, as shown here, 34, 21, 35 converts to 34.35972 degrees in decimal format, or 96.39167 degrees converts to 96 degrees, 23 minutes, 30 seconds. Conversions of degrees to decimal form is also shown in this graphic. Conversion from decimal format, 63.31784 degrees, 2 degrees, 63.1904 seconds is shown in this graphic. Remember, it is always required to convert to decimal form before using most calculators, unless they are pre-programmed to make the degrees to decimals and vice versa conversion. Radian measure is another definition of angular measure and has proven quite convenient for extensive calculations, such as those involving circular curves and statistical analysis of sets of angles. The basic relationship of radians to degrees is shown on this graphic. Remember to convert degrees to decimal form when converting to radians. The most commonly accepted unit of area in land surveying is the acre, which contains 43,560 square feet. Other units of area and their relationship to acres and square feet is shown on this graphic. Conversions to corresponding units may be made by inspection of this table in your workbook. This portion of the unit will center on random error. I must caution the viewer that time prevents a complete discussion of all types of survey measurement error other than random. I recommend additional study outside the training video to completely understand error in survey measurement. A random measurement error is defined as the difference between a measured quantity and its true dimension. Human limitations, limitations on the manufacturing precision of survey instruments, and other uncertainties act in concert to prevent ever making a true measurement. Therefore, it can be stated that no measurement is exact and will always contain some error of unknown size. It is impossible to prevent error, and it should be an objective of the surveyor to recognize error and control it. Random errors are unavoidable. They follow laws of probability and tend to be of either sign and are quite small. Hence, they tend to almost but not quite cancel each other out. Making a set of measurements of the same quantity and then studying the results will indicate differences in value and express the reliability of each measurement by showing its difference from the mean of the set. An analysis will determine and quantify the mean or most probable value of the set to truth. However, before we explore this process, let's define some of the terms involved. In the first term shown on the graphic is most probable value. The most probable value is also the arithmetical mean or average of the set. The next term considered is shown in this graphic. It is called the residual and is the difference between a single measurement and the most probable value. Residuals play a key role in the analysis process that we will be looking at in a minute. This graphic shows the next term to be defined, the standard error. This factor defines the value or accuracy of a set of measurements and sets the limit within which 68% of the measurements will fall. The probable error modifies the standard error and is shown on this screen. It fixes the limits between which 50% of the measurements within a set would fall. Other modifications are shown and are known as the 90% error and the 95% error, which set limits within which 90% and 95% of the measurements, respectively, will fall. The most probable value of a set of measurements is the mean or average. As you will see, the mean is derived from the set, so it too is subject to random error. The mean is often accepted as a final result, so its dependability should be quantified. The equation for standard error of the mean is shown on this graphic. The standard error of the mean can be modified to reflect the 90% error and the 95% errors, also by applying the same modifiers shown in the last graphic. To put all of our foregoing discussion of equations and error computation into use, let's take a look at the current graphic. Totaling the lengths equals a summation of 6,777.42 feet. This divided by 6, n number of measurements, yields a most probable value of 1,129.57 feet. Determining the residuals, squaring them, and then totaling them equals a residual summation of 0.0168. When this figure is plugged into the equation for standard error of the set, the result is plus or minus 0.05 feet rounded to 2 places. This means that 68% of the measurements within the set will fall between 1,129.52 feet and 1,129.62 feet. The standard error of the mean was found to be plus or minus 0.02 feet, which signifies there is a 68% probability that the true distance lies somewhere in the range between 1,129.55 feet and 1,129.59 feet. Until this point, we have been discussing errors affecting only a single measurement. Random error also affects measurements resulting from combining 2 or more quantities by computational processes. A sum or product of separate measurements, each with its distinct random error, will have a total random error influenced by a composite of the individual errors. The first propagation of error process we will look at is identifying the error created in a sum of a number of separate measurements made under different independent conditions. A line has been measured in 4 segments, each segment under different conditions, yielding a different standard error for each segment. In this graphic, the estimated standard error for the sum of the measurements is determined to be plus or minus 0.054 feet. Next to be considered is the error developed in multiplication of measurements, such as for determining areas. This graphic illustrates the determination of expected error in a calculated product. The completed calculation states the product has a standard error of plus or minus 3.02 square feet. This error occurs when a series of measurements made under the same conditions are totaled up. Each of the measurements are subject to the same random error and tend to cancel each other out. The equation for this computation is shown in this graphic. This process states the distance, 2,175 feet, was measured with an accuracy of plus or minus 0.12 feet. I would remind the viewer again that random error is inevitable in survey measurement. Live with it and learn to identify and control it. Do not waste time trying to eliminate it. Algebra can be considered an extension of arithmetic, in which symbols represent unknown quantities related to known factors of an expression. All knowns and unknowns are integral to operations that are consistent to numbers in the expression. I included the following discussion to develop a basic awareness in solving for unknowns and to develop the worker's skill in working with negative numbers. Numbers in mathematics are of three categories: positive numbers that are greater than 0, negative numbers that are less than 0, and 0 itself, which needs no explanation. As shown in the sketch, signed numbers to the left of 0 are considered negative and are always preceded by a minus sign. Numbers to the right of 0 are positive numbers and may or may not be preceded by a positive sign. The absolute value of a number is its value without reference to a sign. Thereby, positive 6 would have the same absolute value as negative 6. In working with signed numbers, there are certain guidelines to follow in avoiding blunders and getting answers with incorrect signs. First, let's consider the addition of signed numbers. As shown in this screen, the sum of two positive numbers is positive. 46 plus 34 equals 80. The sum of two negative numbers is negative. Minus 21 plus minus 76 equals minus 97. The sum of a positive and negative number will be: first, determine the difference in absolute value of the number. Positive if the absolute value of the positive number is larger. 82 plus negative 31 equals 51. Negative if the absolute value of the negative number is larger. 26 plus negative 67 equals negative 41. The next case of signed number operations, the subtraction operation, the rule is rather uncomplicated. When subtracting one signed number from another, simply reverse the sign of the second number and then add the two numbers using the addition rules just discussed. Multiplication of signed numbers is also a very simple rule to follow. The product of two positive numbers is always positive, while the product of a negative number and a positive number will always be negative. However, the product of two negative numbers will always be a positive number. The last case of operations with signed numbers concerns division. The rule for division is the same as multiplication. The quotient of two positive numbers is positive, while the quotient of two negative numbers is also positive. The quotient of a negative number and a positive number is always negative. An algebraic equation should be thought of as a math statement that is balanced on both sides of its equal signs, or quantities on the left side must equal the quantities on the right side. Each side of an equation may be modified, but remember to modify each side by exactly the same degree and quantity, or do the same thing to both sides. An equation is used to find the value of an unknown number from its relationship to the known values in the equation. The ability to visualize a mathematical problem in words and then form it into an equation is a valuable skill for the surveyor. For example, in this graphic, unknowns are identified as B or Z, and then equations are formed from the word statements to reach solutions. As shown by the two examples in this graphic, equations are formed from conditions set by a word statement. A number divided by 3 plus the same number times 7 equates to B divided by 3 plus B times 7. A number plus 212 times 8 plus the same number divided by 34 equates to Z plus 212 times 8 plus Z divided by 34. When working with more than two quantities in an algebraic expression, perform the indicated work in the order presented in the next graphic. Work from the left doing multiplication and division. Work from the left again doing addition and subtraction operations. For example, 267 times 6 plus 96 divided by 4 minus 4 times 12 minus 9 reduces to 1,602 plus 26 minus 48 minus 9 equals 1,571. The second example, 301 minus 22 times 14 plus 81 divided by 27 minus 76 reduces to 301 minus 308 plus 3 minus 76 equals negative 80. In algebra, it is often necessary to group terms and consider a whole group of several groups as a single term. Grouping is indicated by parentheses, brackets, or braces. The plus or minus sign in front of each group applies to each term in the group. Rules for removing parentheses are presented in this graphic. If parentheses are preceded by a positive sign, they can be removed without changing the signs of terms inside. If preceded by a negative sign, remove the parentheses by changing the sign of every term within the group. It is much like multiplying a group by +1 or by -1. First, 5x plus 3y minus 4z equals 5x plus 3y minus 4z. Second, 5x minus 3y minus 4z is reduced to 5x minus 3y plus 4z. Oftentimes there are several groups in one problem. In this case, remove the inner set first and then the outer set, and so on, following the prior stated rules. An algebraic equation contains signs for some of all the four mathematical operations: add, subtract, multiply, or divide, and also letters that are substitutes for numbers. These letters are called variables, and when replaced by actual number values through substitution, the equation is simplified. When simplifying an equation, simply plug assigned numbers into the variables and then combine the terms following the rules of order of operations. As shown in this graphic, make the following substitutions. Let A equal 12, B equal 6, and X equals 7. X plus A times B minus B equals 7 plus 12 times 6 minus 6, or 7 plus 72 minus 6 equals 73. Solving equations. Equations are generally solved by picking out one of the unknowns, isolating it, and then solving for it. Something to keep in mind: it is much easier to manipulate the variables and reach a formulated solution prior to substituting actual numerical values. For example, let's solve this equation for r, assuming we already know the value of a. Let's follow the solution on the graphic, keeping in mind to do the same thing to both sides of the equation. Area of a circle is a equals pi times radius squared. Solve for radius. Let a equal 9,503 square feet. Rearrange. R squared equals area divided by pi. Extract the square root. R equals the square root of area divided by pi. Up to this point, equations and the processes discussed have been elementary first power equations. In many problems, squares, cubes, and higher powers will occur. A quadratic equation is a function which contains the second power of one unknown. A quadratic equation useful for surveying computations is generally written as ax squared plus bx plus c equals 0. A, b, and c are generally numbers, with x remaining as a value sought. For ease of solution, the quadratic equation is reduced to the quadratic formula shown in this graphic. There is a plus or minus sign in front of the square root sign. This will yield two different answers when solving a quadratic. You must determine by a careful analysis of the problem which is the correct answer. Familiarity with algebra gives the surveyor the ability and tools to reduce a problem to a logical solution by arriving at and correctly setting up an algebraic formula. It is much easier to work with equations before they have the numbers plugged in. When the solution has been found and the equation set up, then and only then should the numbers come into play. I highly recommend keeping your calculations as simple as possible. Don't add any unnecessary steps. An extra step just increases your chances of making a blunder or calculation error. Geometry is as old as civilization. We know the Sumerians and the Egyptians had the knowledge of and applied the principles of geometry. In fact, a translation of the Greek word geometry means earth measurement. Geometrical facts, figures, and formulas are essential to understanding and applying mathematical processes to surveying. The following definitions will provide a brief review of geometric principles. We will start our discussion with some of the basic corollaries or laws of geometry. Let's first talk about lines. As shown in example number 1 of this graphic, straight lines extend to infinity in both directions. Example number 2 shows that if straight lines in the same plane meet, they are intersecting lines and share a common point. Example number 3 proves that if two straight lines have no common point, they are parallel lines. A line extending to infinity from a defined starting point is a half line, as shown in figure number 4. As shown in figure number 5, a line starting from a defined starting point and ending at another defined point is a line segment. Angles are formed when two half lines or segments are drawn from the same starting point. You can also form an angle by rotating a half line about its starting point, which is also the vertex of the angle formed. The dimension of the angle formed is measured and stated in degrees or radians. This graphic shows the different types of angles and their definition. As shown, angles are classified as acute, less than 90 degrees, right, exactly 90 degrees, obtuse, between 90 and 180 degrees, straight, exactly 180 degrees, reflex, between 180 and 360 degrees. A pair of angles that total 90 degrees are called complementary angles. This means that 37 degrees would be the complement to 53 degrees. Two angles that total up to 180 degrees are defined as supplementary angles. In other words, 68 degrees would be the supplement to 112 degrees. In geometry, certain basic theorems or statements exist to serve as basic rules. I am presenting some of the rules in the next few graphics to give you some more basic geometrical concepts about lines and angles. Proof of the theorems presented has been omitted from my presentation. The rules are sufficient to stand on their own. Rule number 1. When two lines intersect, angles formed opposite to each other are identical. Thus, angle 1 equals angle 3, and angle 2 equals angle 4. Rule number 2. When two parallel lines are intersected by a transverse line, the alternate interior angles formed are the same. As shown, angle 1 equals angle 3, and angle 2 equals angle 4. Rule number 3. When two parallel lines are intersected by a transverse line, the corresponding angles formed are the same. As shown, angle 1 equals angle 5, angle 2 equals angle 6, angle 3 equals angle 7, and angle 4 equals angle 8. Rule number 4. Two angles are the same or supplement each other if their corresponding sides are perpendicular. As shown, angle 1 equals angle 2, and angle 2 plus angle 3 equals 180 degrees. Almost all surveying operations and computations involve geometrical figures. Therefore, I will be presenting most of the basic ones encountered in our work, along with a brief look at some of the properties and rules of the figures. Let's start with our old friend, the circle. This often used figure is the basis of horizontal curve computation and layout, as explained in another of the video units. A circle can be defined as a closed curve in the same plane, every point of which is the same distance or radius from a point within the circle, called the center of the circle or radius point. In this graphic, the basic portions of a circle are identified. If you traveled entirely around the circle, starting at point A and returned to point A, you would have walked the circumference of the circle. If you went from point A along the straight line to point C, which is the diameter which bisects the circle. The line from the radius point to point B represents the radius, which is 1/2 the diameter. Back to walking around the circle again. The distance from point B to point C describes an arc. Also, if a line is drawn from the center of a circle, line from RP to point F, perpendicular to a chord, it bisects the chord and the arc defined by the chord. This important rule comes into play when working with circular highway curves. Sector and segment are another two elements of a curve that should be familiar to a surveyor, as they are often used to calculate areas of surveys with curved boundaries. As shown in this graphic, the sector of an arc is the shaded wedge-shaped figure bounded by its arc and two radial lines. Its area is determined by the formula shown in the graphic. Sector area equals radius squared times delta expressed in radians divided by 2. Note on the graphic that the radius of the arc is 139 feet and the delta angle is 47 degrees 30 minutes. Let's stop the tape at this point and work the problem. Okay, you have turned the tape back on. Let's check your answer. I get 8,009 square feet. What did you get? This screen shows the second curve element under discussion, the segment of an arc. It is the shaded area and is defined as bounded by its arc and the chord for its arc. The area of a segment is calculated by the method now on screen. First, determine the area of the sector of an arc OPR by the formula just discussed. Sector area equals radius squared times delta expressed in radians divided by 2. Then determine area of triangle OPR. The formula for this triangle is radius squared divided by 2 times sine delta. When both areas are computed, subtract the area of the inscribed triangle from the sector area, thereby finding the area of the segment. Letting R equal 421.25 feet and delta equaling 28 degrees 31 minutes and 15 seconds, shut the tape off and compute the area of segment OAC. Then turn the tape back on to check your answer with mine. Okay, I got 44,166 square feet for the sector area and 42,365 square feet for the inscribed triangle. Subtracting the triangle from the sector gave me the area of the sector, 1,801 square feet. Is this what you got? Some other formulas dealing with curves are shown in this graphic. They are circumference equals 2 times pi times radius. Area equals pi times radius squared. Radius equals 0.56419 times square root of area. Diameter equals 1.12838 times square root of area. Well, this pretty well finishes the discussion of circles, so let's move on and discuss some more geometrical figures that you will likely encounter in your surveying and test-taking activities. A polygon defines any figure bounded by 3 or more line segments. A polygon may have any number of sides as long as they are broken. That is, segmented and enclose a figure. the simplest polygon is the triangle having the least number of sides, 3. The triangle is one of the most used figures in surveying and survey calculation. It has many configurations and classification. Let's take a look at them. Triangles are classified in 2 different ways, by sides and by angles. First, we will look at the triangles classified by sides. The first of 3 types of triangles classified by sides are shown as figure 1 in this graphic. This triangle is called an isosceles triangle and is distinguished by having 2 equal length sides. Note that the unequal side is called the base and that the angle opposite the base is the vertex angle. The second type of triangle in this classification is shown in figure 2 and is called an equilateral triangle. This one has all 3 sides of equal length. The third and last triangle in this classification is the scalene triangle, and it has 3 unequal sides as shown in figure 3 in this graphic. Triangles are also classified by the angles they contain. There are 3 types of triangles within this classification: acute, obtuse, and right. We will look at figure 1 in this graphic and discuss the acute triangle first. This type of triangle has 3 acute less than 90-degree angles. Type number 2, figure 2, has 1 angle of the 3 that is an obtuse triangle, more than 90 degrees, less than 180 degrees. The other 2 angles of the triangle are always acute. The last type in the angular classification has 1 angle that is exactly 90 degrees. The other 2 angles of the right triangle will always be acute. As shown in figure 3 of this graphic, the side opposite of the right angle would be called the hypotenuse. The right triangle is the workhorse of survey measurement and calculation and will be discussed in greater detail later in this video unit. The next few graphics show polygons other than triangles. These are polygons having more than 3 sides. Familiarity with any of these polygons will prove useful to the surveyor and test taker. Before we look at any of the polygons, let me state a golden rule concerning interior angles of any polygon. The sum of the interior angles of any polygon is equal to 180 degrees times the total number of sides less 2. This formula provides a check of interior angles measured for a closed figure. The first polygons to be considered are the ones defined as regular or having all sides and angles equal. As shown in these next graphics, polygons are named for their number of sides. A formula for area computation is also shown in each of the graphics. The first regular polygon to be considered is the equilateral triangle, all 3 sides the same length. Its area is easily computed by the formula area equals 0.25 times n, number of sides, times side squared times cotangent of 180 divided by n. Also shown is the symbology for the formula, where we let n stand for the number of sides and s for the length of the sides, which are identical in this case. The next regular polygon to be discussed in the series should have been the 4-sided square. However, its properties are well known, so let's move on to the pentagon or 5-sided figure. This graphic shows a regular pentagon, 5 equal sides and angles. Computation of its area is also by the same formula. In fact, this formula can be used to compute the area of any regular polygon regardless of the number of sides. Again, n equals number of sides and s equals the length of the sides, which are identical in length. This graphic shows a regular hexagon, 6 equal sides and angles. Computation of its area is by the same formula. There is no need to look at any more regular polygons, as the pattern of construction and area formula should be very clear by now. Surveyors should be interested in the additional polygons discussed in the next few graphics. They consist of various forms of quadrilaterals or 4-sided figures. The square and rectangle will not be discussed, as they should be very familiar to the viewer. The parallelogram is a quadrilateral with the opposing sides equal and parallel. All its angles are different than 90 degrees, except in the case of a rectangle, which has 90-degree angles. A parallelogram that is not a rectangle can also be considered a rhomboid. As shown on the graphic, the rhomboid's area can be calculated by area equals A times B times sine theta. A and B symbolize the length of their respective sides. This graphic shows a parallelogram or rhomboid with all sides of equal length. This figure is a sketch of a rhombus. Its area is computed from the formula area equals B squared times sine theta, letting B equal the length of the sides. A quadrilateral with only two of its sides parallel is named a trapezoid and is shown in this graphic. This configuration is one heavily used for engineering design and layout. Its area is determined from the following formula. Area equals h divided by 2 times b plus b prime. In this formula, b stands for the length of sides and h is the altitude. A trapezium is defined as a quadrilateral with none of its sides being parallel. Its area is calculated by the equation area equals d times h over 2 plus b over 4 times h prime plus h double prime, where b equals the bottom width, d equals the top width, h the first altitude, and h double prime the second altitude. The irregular pentagon is the last of the plane geometric figures I will discuss. This figure has 5 sides, none of which are parallel or equal in length. Also, none of its angles are equal. Its area can be calculated by the equation on the graphic, which is the same one discussed in the last graphic. I have reviewed many of the basic and fundamental facts found in geometry. Time prevents a complete review of a subject that takes many hours of study and practice to fully appreciate. However, the aspiring surveyor and/or examinee should further pursue the study of geometry, as I have only touched the surface of the subject. There are certain geometrical constructions that have a great value in solutions of surveying problems and calculations. Well, as much as I enjoy talking about surveying, math, and numbers, I feel that perhaps this is a good time to take a break. When we come back, we will launch into a study of trigonometry.